I should be recording this. This is number 2 from the book. Today is the 7th, and this one's rather boogery. What's my expression for VIY? VI sine theta. Okay. I know that I have no acceleration on the x. I know that acceleration on the y equals negative g, or negative 9.81 meters per second squared. Okay. Do I have a delta x? I do. I do. So delta x is 301.5 meters. Delta t I'll just leave sitting right there because we know that's going to be the bridge that connects our axes. Do we have a delta y? Well, actually we do. So let's talk about this, and let's talk about thinking about the situation. That's why these problems are so hard. Because you have to think about what's actually happening with this object. So this object is coming off of the ground, going up some distance, and landing on the ground. If I call these overall variables for x and y, what's my overall delta y? 0. 0. And that's really critical because that enables you to do some funky, cool, tricky stuff when something disappears. All right, so taking that into account, knowing that delta t is going to form our bridge, let's see where we go with this. Well, I know that on the x-axis I don't have acceleration, so delta x equals VIx delta t equals delta x over VIx, and I can further substitute. So I've got that expression, and I can easily build an expression on the y-axis because I know that delta y overall is equal to VIy delta t plus 1/2 a sub y delta t squared. So I can plug in my delta t value there. I can plug in my expressions for VIy. Times delta x over VI cosine theta plus 1/2 a sub y over delta x VI cosine theta quantity squared. Okay, I can do some simplification here, obviously. Well, let's see. VI's cancel. Sine divided by cosine gives me tangent. So delta y now equals delta x tan theta plus 1/2 a sub y times delta x squared VI squared cosine squared theta. And I know that that goes away. Now let's ask. So wait, I'm trying to solve for maximum height. This doesn't get me maximum height. Did I just go down a rabbit hole? This is the approach we've used in the other problems we've done. I know we're only on number 2, but it seems like we do this all the time. Well, is all of what I put here true when we consider the flight path of this object overall? Yep. Sure enough. Did any of you do this and get to here? Oh, okay. Good. Didn't get you where you wanted to go, huh? So let's talk about what we need to find maximum height of an object. There is something that is true. So, let's go ahead and look at this little piece of flight path here. Here's maximum height. There is something that is true at maximum height that isn't true anyplace else on flight path. I'm going to pause this and give you a moment to talk to one another. So we know that at that top of height moment, the vertical velocity goes to 0. Well, crap, I completely overcomplicated this, didn't I? Because do I have an equation? Can I treat this on just the y-axis? Oh, duh. What was I thinking? Huh. Silly, silly Moser. Okay, so if I know that VF, and I'm going to put this, VFY at y max, it's a whole lot of subscripting, equals 0, and I want to know delta y, and I have a sub y, negative g, negative 9.81 meters per second squared. Do I have an equation that will connect initial and final velocity, delta y, and acceleration? I most certainly do. VFy squared equals VI y squared plus 2a delta y. And this is delta y. This would be max. Oh, cool. That wasn't so bad. Is it all over yet? Oh, crap. Well, let's do a couple of things here. So we want to solve for delta y max. So that would be VFy squared minus VIy squared over 2a equals delta y max. And VFy squared we know is 0. So that's 0 minus, well, what is VIy, did we say? VI, this would be VI squared sine squared theta, whole thing over 2a equals delta y max. Oh, okay. Whew. Excellent. Are we done? Do we have a problem? What's our problem? Talk at your tables. That's the problem. We don't have VI. We don't have VI, so it's fine to say negative VI squared over sine squared, or times sine squared theta over 2a equals delta y max, but we don't have VI. If we did have VI, this would be a piece of cake. So what do? We create an expression for VI. Where are we going with this? We're creating an expression for VI. So let's create the expression for VI, and I'll switch colors once again just to keep things interesting. So we know that delta y for, now this is really important. Note that I marked overall and top of flight, because everything that we are writing in this equation has to relate back to the moment at top of flight, because we're relating it in a single equation. Everything that we're writing in this equation has to be true overall. Delta y overall and delta y at top of flight are not the same. But we can write but the VI is the same the whole way through. So the VI was always the VI. You can't go back and change the VI. The acceleration on the y-axis is going to change. It's going to decrease, zero out, and increase. But VI didn't change. So we can create an expression from the overall behavior of the object and plug that back into the equation that describes the behavior of the object at a moment in flight. So let's go ahead and do that. So that is 0 equals delta x tan theta plus, and I'm going to do a little bit of combining here, ay delta x squared over 2 vi squared cosine squared theta. I am looking here to isolate vi, so I'm going to do 0 minus delta x tan theta equals ay delta x squared over 2 vi squared cosine squared theta. And I can multiply. I'm gonna shortcut the showing the steps if you're okay with that, or do you want me to do every little piece? Every piece? Okay. I'm going to verbally discuss what I'm doing here. If I multiply both sides by vi squared, obviously this has gone away. I have vi squared delta x tan theta. I can then divide both sides by the delta x tan theta, and what I get is this beauty. Vi squared equals a sub y delta x squared over. Now you have to be careful here because this was all negative. So I'm going to keep a -1 here, and that will matter. -1 delta x tan theta times 2 times cosine squared theta. What a hideous, awful mess. Oh, we're not even close. You should see the calculations they did to get people to the moon. All done with slide rules, I should mention. Okay, so we have, or we can just do, oh, yeah, that's what we can do. We're good. Okay. Negative of square root of ay delta x squared. Oh, and we can cancel out 1 delta x. So we can make that ay delta x over -1 times tan theta times 2 times cosine theta. That whole thing times sine squared theta over 2a gives us delta y max. Now, what's really funny, this isn't one of them. I was going to say, there are, no, shut up, Moser, never mind. That's not the case you're thinking of. That'll give us delta y max. Now, is it legitimate to solve for vi and plug in a number? It's in essence what you're doing anyway. But you should be able to show the plug-in because of the fact that there come points where we have to do multiple substitutions, and I want you to get good at substitutions. Okay, any more questions on this one? It's a little bit ugly, but boy, it feels really good once you solve it. The big takeaway from the ones like this, it's okay to go down a blind alley. And, then you step back and you evaluate everything that's in the equation that you've just done. And you go, okay, well, wait, is it all true? Does it all relate? But does it answer the question? Is there another point in this object's motion where we can answer the question that we need to answer? So, okay, I'll let you keep pushing.